Hi, in this video, we're going to take a look at analyzing spatial temporal disease data. All right, so we're in the situation where we have locations in terms of a real data. So we have something like neighborhoods, counties, states, countries, like that. That's our spatial aspect. And we have time in terms of years for this video. So what we want to do, we want to analyze the spatial temporal combination of the data to see what's going on, see if we can make some statistical inferences. All right, so what we're going to do, we're going to take a brain cancer data example from Applied Spatial Data Analysis with R, Chapter 10, Disease Mapping. This is section 7 of that chapter. Here are the authors' names. Here is the textbook's website, and you can download the textbook for free if you're a UCF student. All right, so now let's go ahead and jump in on it. All right, so when we've got spatial temporal data, we have our data values are connected both to a time and to a location. In this example, those locations are going to be counties. Now, when we have spatial temporal data, things can get complicated like right out of the gate. You look at it, I have all these locations, I have all these times aspects. So simultaneously, I have spatial statistics and I have time series going on, and I need to have them together. All right, so how do I recommend that you tackle this? Well, my advice to you overall is first and foremost to analyze things from a univariate point of view. So not considering time, not considering location at all. So you just take the aggregate of over time and space, do the analysis of that. So that way you start understanding what's going on. Next, what you do, in my advice, is that you analyze either the time series aspect or the spatial statistics aspect, whichever one's easier for you. Now that will depend on your data and your experience with spatial statistics and time series. Whichever one's easier, go for that one first. Then, after you feel like you understand what's going on, go on to the next one. So if you did time series, go to spatial statistics. If you did spatial statistics, go to time series. Then, after you've gone through those 3 steps, start trying to understand the spatial temporal aspect overall without any aggregation. All right, so in the example that we're going to work through here with the brain cancer for New Mexico in the late 70s to early 90s, we're going to say that E sub IT is the expected number of cases in region I and year T. O is for the observed number of cases with respect to location and time. Theta is the relative risk. Mu is the mean of the Poisson distribution. So we're going to assume that our observations are from a Poisson distribution. Now, if that doesn't work out for us, if we see that things are over dispersed, we could switch to negative binomial if we needed to. And we're going to say that we're going to make the assumption that mu is equal to E times the expected number times theta, the relative risk, and the observed is a Poisson random variable on mu. All right, now let's take this a little, so we're going to go a little bit deeper into this. For actual modeling, when I'm actually building my models, I'm going to say that the observed is a Poisson distribution of expected times relative risk at location I time T. Now, my relative risk, what we're going to do, we're going to model the relative risk, specifically the log of it, as something that looks a lot like linear regression. So we have an intercept, we have a coefficient times a covariate. Now here, pay attention to the subscript. That I means that's for location. So there's a covariate at the location. Then we have V sub I. This is going to be the spatial random effect. And then W sub T, this is going to be the temporal effect. on there. Now we're going to continue in this and say that our spatial random effects are conditional autoregressive, and here it's just the parameter that we have. We're going to make the assumption that our temporal effect is a random walk of order 1 with constant variance. We'll go ahead and make a further assumption for our Bayesian statistics point of view, is that both of the sigmas are inverse gamma. That's for our priors. So x of I is our covariate at the location, v sub I are the spatial random effects, and w sub t are the temporal effects for that year. All right, so let's go ahead and start tackling this. First, I'm going to load the New Mexico brain cancer data, and this is coming from the textbook's website. Now, what I'm going to do, I'm going to aggregate by year. So I chose on this first step to analyze the time series aspect first. Okay, so what I'm doing is I'm taking the dates. So here, the dates that they have are just year. And for R to fully handle things the way I want them to, I want to go ahead and have year, month, day. And so I'm doing a paste statement on that. And then I'm converting that to date. And then I connect the observed values to the year. So here I'm representing New Year's Day for the year, and then I convert it over to a time series object. Now for the expected value, I do exactly the same thing I did for the observed. Now what I'm going to do is I'm going to take the sum over all of the years. So I'm using apply yearly. So for over the entire time series, I'm going to add up for that. I'm going to add up for each year. And now I have the yearly observed and the yearly expected. Now what I'm going to do is I'm going to take the ratio of the observed and expected for each year and get the yearly standardized mortality ratio. And so now I have aggregated it into time series. And when I look at this, I'm not considering the spatial aspect at all. And so now I'll just go ahead and create a data frame for me where year is the year, observed is the observed amount, expected is the expected, and the standardized mortality ratio is in there. Do a little bit of data manipulation to get into the format that ggplot likes for plotting. And now I run ggplot. And so we can see that it looks like we had a linear growth for the expected value. All right, so when we're computing the overall theta, the overall relative risk, we're treating that as a constant. And so when I look at this, what I think is going on is that the population grew pretty consistently, and we're using a constant for our overall relative risk. From a course point of view, that's our way to calculate expected values. So here I conclude what's going on is that this growth is from the population growth, more than likely. I don't know for certain. I could get the original data, talk to the person who collected it, and documentation, and see some more, but I'm pretty sure I'm right on this one. Now for the observed, we can see the observed counts year by year over. Now this will be over the entire state. Now look what happens with the SMR. All right, so we see that we have a nearly constant straight line for expected. And when I see the observed, remember that SMR is observed divided by expected, and we see the same shape. It's a little bit different, but overall you can see each of these bumps matching up between observed and SMR. Okay. All right, so now that gave me an idea of what's going on, that that SMR is pretty much the observed value because of that linear aspect of expected, and expected is a nearly constant slope linear growth. All right, so now let's go the other way. Before, I aggregated over the years and remove spatial aspects from it. Now I'm going to aggregate over the spatial locations and going to drop out the year aspect. All right, so here I'm just going to go ahead and group by the county. So FIPS is an ID number for each county in the United States. I'm going to go ahead and run a summary function. Notice that this is summarized with an S. I could put a Z or an S in there. The tidyverse accepts both, in case you're using like the British spelling or the American spelling. And here I've got the sum. And now here I am using piping and dplyr. So I'm going to get a tibble back. I don't like tibbles. They're not compatible with all packages, so I prefer to work with data frames. Boom, I'm converting the tibble to a data frame. Now I'm calculating the standardized mortality ratio for each county over the entire study time period. I'm changing the FIPS column name to ID to be consistent with other labeling within the data set. Here I am permuting the rows to make sure that everything lines up correctly off of this, because I need to make sure that the rows are in the same order as they will be when I start handling the spatial polygons data frame in a moment. If I mess up the rows on this, everything is messed up for my analysis. And so this step here of setting the row names and then permuting them about, all of that is done for here. Here I'm extracting the ID, and I'm making sure I have the ID here, which is extracted from within the data frame, and I use the external ID vector from here to make sure that things are in the right order. This was a little bit technical of a step. And so now, just to make the visualization easier to interpret, I go ahead and use quartiles to determine the coloring for observed, expected, and SMR. So now I'm building the spatial polygons data frame. So I'm taking the spatial polygons that I already have established. I'm using the aggregate data in the data slot of the spatial polygons data frame. And I am matching on the ID to make sure things work, that things match up row by row the way I want them to. And now I'm actually doing the plotting. All right, so here I've got, I can see darker red, darker red. So this is the number of observed cases. So something that is going to come up in a little bit is that you can see that we have darker red here closer to Los Alamos. Now let's look at the expected. Now something that's important is that you'll see similarly darker colors in the same location in terms of expected. Now let's go ahead and scroll down. Let's look at the same plot, but this time with the standardized mortality ratio. And now things don't look as consistent in terms of the coloring. All right, so right now, off of the spatial effects, I'm kind of feeling like there might be something going on closer to this region. But I also notice that the observed and the expected, when I take the ratio of them, the ratio doesn't seem as strong as I thought. All right, so now we can go through and do the actual spatial temporal plotting if we want. and you want to, you can go through and try to track through. This is a lot. I have all the counties in New Mexico. Oh, well, correction, that 2 counties were merged together because there was lacking data, but otherwise I have all the counties in New Mexico over all these years. So I mean, it's a lot to have. Like, if I want to analyze this, I have to look at one county on its own, ding, 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 across. Also, remember, I'm going by year and county, and we're talking about something where we're talking about a disease that we're not going to have that many cases. Look at how much white is on there. So in these rarer events, one observation can be a big deal. So one observation increase or decrease can have a huge impact on anything that uses proportions. And so it's rather volatile to use this nuance of data. So we have to be careful. All right, so now let's go ahead and visualize the yearly SMR. And we see that it's going up and down. So when standardization, like 1 is like that null hypothesis baseline. And so it looks like earlier years, I've got like a bunch below, later years, I have a bunch above. All right, so now what I want to do is I want to construct a Bayes X model. So this is a star model, and we're going to use the R2 Bayes X package. First thing I need to do is take my neighbor data that I have and change that to a graph format, which this package needs to work. And so I'm taking my neighbor data for the counties that came with the data set, and I'm converting over to the graph format that this package wants. Now I'm going to drop that into my Bayesian statistics modeling. All right, so when we look here, what we're going to do, we're going to take our observed number. We're going to assume that it depends on the inverse distance from Los Alamos, the smooth yearly effect, and the smooth spatial effect. We're adding on an offset for the expected values. We're going to use a Poisson distribution for this, and we're using our data as a data frame. And we're going to go ahead and append on the output onto the NMF dataset, which came loaded when I loaded the data from R. All right, so now let's go ahead and visually look at the temporal trend. All right, so when I look at this, I can see that here is the mean, sample mean. Or sorry, this is the Bayesian Monte Carlo Markov chain mean. Here is my 97.5 upper bound of my credible interval. Here is my 2.5% lower bound of the credible interval. And you'll notice that 0 is in there almost the entire time. Or I look at this and I conclude that the temporal aspect probably could be removed. Let's keep going. Let's go ahead and run a plot of this. So I'm going to go through, I'm going to plot the temporal or the spatial effects by county. So here's the spatial effect. And I can see that the blue, I have positive numbers close to Los Alamos, and the red, I have positive for my spatial effects. Okay, so that kind of like adds something to the the hypothesis that being close to Los Alamos would connect with brain cancer. But let's go ahead and take a look at the inverse distance plot. So what I did here was I extracted the Monte Carlo Markov chain simulation values for the inverse distance from Los Alamos National Laboratory, and I just plotted it here. So I've got the inverse distance, and then I've got the credible interval from Bayesian statistics. And you'll notice that in my credible interval, the entire time, 0 is in there. All right, so I conclude that inverse distance probably could be removed from the model. You know, I feel like it's making the model more complicated by keeping it in there for considering the informative value. All right. All right, so I played around with it, and I was convinced it's time to reduce this model. Now, reducing the model is not in the textbook. It's something I did on my own. All right, so what I did was I created a data frame to indicate the terms in the formula of the model. So on this line, this has the Los Alamos distance, the year, and the spatial effect. This line, the formula uses yearly effect and spatial effect. This one uses inverse distance and spatial effect. And then these three, or this one, only has spatial effect. This one only has the temporal. This one only has the inverse distance. And so, and this bottom one is the intercept model because it's blank. All right, so this was a way that I built up a way to programmatically go through all 8 possibilities. You'll notice that this first one is redundant with the model that we already built, but to make things simple, I just went ahead and ran it. All right, so I did some kind of slick computing, but ultimately I just used a paste statement to build the formula that uses each of those rows. And I have the offset like I had before, the Poisson distribution like I had, and we're using our data in the data frame. So I'm going to build 8 models. Now, when I did this, I looked at each of these one by one. And I looked at inverse distance, I looked at spatial effect, and I looked at temporal effect. And on all cases, I concluded that from the credible interval containing 0, I concluded that all of them should be removed from the model, which means that the intercept model is the best model of the 8. All right, so that from a statistician, I conclude that inverse distance from Los Alamos is not statistically significant for brain cancer. I conclude that spatial effects in terms of counties across New Mexico are not statistically significant. And I conclude that for the years evaluated, there is no temporal aspect that is statistically significant. And so whatever's going on with brain cancer in New Mexico, we don't have full information. Now, when we looked at that map, though, we did see a difference. But that I believe that difference can be accounted for by the increased population, which we see in that expected value time series chart. We see an increased number of cases, but I conclude that's more from the increased population than from anything else we have in the data. Now, it's possible that there is a spatial aspect. It's possible that there's a temporal aspect. It's possible that there's an effect from Los Alamos, but the data that we have is not strong enough to be convincing of that in terms of statistics. Therefore, I conclude that the data we have gives us no further information about brain cancer in New Mexico over those years, aggregated over counties. Well, that's all I've got for you. Take care and goodbye.